fortunately, one last presentation. Welcome Bharat Rajagopalan, Director of Strategic Marketing at ST Microelectronics. He is the Director of Strategic Marketing at ST Microelectronics, responsible for developing the company's strategy for augmented reality, leveraging ST's broad technology and product portfolio. Bharat is a veteran of the electronics industry, having served in technical, managerial, and executive roles in research and development, manufacturing, product development, and marketing. He's also serving as the inaugural chair of the LASAR Alliance, for which he was instrumental in conceiving, creating, and implementing. Prior to ST, he has held a number of leadership positions, including roles at Microvision, Dolby Laboratories, Texas Instruments, and IBM in semiconductor technology development and manufacturing, display technology development, and imaging systems. Bharat holds a Master of Science and PhD degrees in electrical engineering and an MBA. Welcome.
All right. Okay, so I'm standing between you and happy hour. I realize that. So hang with me, please. Okay, hope they can hear this. And by the way, after a year and a half of doing Zoom, look at myself. I'm so sick of looking at myself. I'm really pleased to look at somebody else in the audience. So thank you for hanging in there and staying here. Great. So today I talked to you about laser beam scanning for augmented reality, and hopefully you'll find this of interest. And we are available for questions afterwards as well. Okay, so we talked a lot today. If you went to the presentations here in the main section, we're all talking about AR, MR, XR. Everyone's talking about glasses. And the real challenge that we face today, and we're pretty far away from, is how do I take everything that you get and experience as a HoloLens or a Magic Leap 2 or any kind of immersive device and put it onto a pair of glasses. And sometimes some of the talks here are like, oh, it's already done or it's here. Well, it's not here. It will be here. It'll take some time, but there's a lot of challenge to overcome, and they can be overcome. It's more of an engineering challenge than an R&D challenge, but nonetheless, trying to pack all that functionality that you get in such an immersive mixed experience into a pair of glasses, it's quite challenging. And what we found is the first order to achieve the challenge, the first thing you have to do is get a very small compact display technology and very good compact optics, or combiner optics or waveguides, for example. And with that, then you can start to build all the layers of the system. The second thing I will say, and I think one of the previous speakers talked about it as well, is that as we look at the content on these devices, the question is, what are people going to do with these things? It's tempting to think that you'll put all kinds of objects into digital object, physical space, and interact all day long. It's not quite clear how that's going to happen. What is clear, however, is informatics, display information such as directions, such as translations, such as weather, text, things that we see every day, useful information we think will be really, really vital and useful and important to people. And therefore, what we say is start with developing systems and glasses that are smart glasses that has informatics and data that you can use every day. And then over time, as technologies mature and they get mature in performance, cost, power, and so on, size, and so on, then you can add those functionality to it. So I would say we're probably several years away from having HoloLens pair of glasses, but the good news is we are pretty far now, well on our way of having a pair of smart glasses with informatics in it. So some of the key requirements for AR wearable devices are really how do you make sure they're usable, how do you make sure they're comfortable, and what is the right performance you need to have. And so from an overall usability point of view, you want to make sure you can wear this inside and outside, or else there's really no utility at all. And you also want to have a pair of glasses that are transparent. You don't want to be wearing sunglasses inside and outside all day long. Second thing, of course, is you want to look attractive, and you want to walk around and not know that you're wearing a computer in your face or wearing a device. You want people to think you're wearing a pair of fashionable glasses. And finally, it has to be very, very low in power, so you don't put a lot of heat in your head or have very heavy batteries. And so from a brightness point of view, what we found is you want to be typically well over 1,300, well over 1,000 candles per square meter, and much higher is preferable, just so we can have very high ambient contrast ratio. Weight is very important, certainly, because the heavier glasses, the more pressure that's on the bridge of your nose, and therefore it gives you headaches and other discomfort. So typically in the eyeglass industry, you want to be less than 70 grams total for the entire glasses that you're wearing. Latency is very important, not so much so for smart glasses, but certainly for immersive applications. You want to be less than 4 milliseconds, so you don't have any kind of motion sickness products. And finally, from a performance point of view, there are 3 key metrics here that we need to think about when design products. First is the field of view. Second is resolution, and third is the eye box. And they're each critical, very, very important things. Resolution is war. People want to have higher and higher resolution, and I will tell you that that's really not as critical as you think it is for certain applications. So for example, if you're doing a pair of smart glasses and you're putting on text and symbols and graphics and overlay, a 720p equivalent is more than enough. However, if you want something more immersive like HoloLens and you want to have, digital objects that are very physically accurate and that are indistinguishable from real objects, then you want to have much higher resolution, of course. Likewise, in the field of view, people think bigger and bigger is better. That is not true. When you're looking at just the directions and instructions and those kind of things, you don't want to look at a big field of view. You don't need a big field of view. It's quite useless, in fact. So being 30 to 40 degree field of view is more than enough. On the other hand, if you want to have something immersive and place all kinds of digital objects in your visual field, then of course you have to have a much higher field of view. So it really depends on what you're trying to accomplish, what you're trying to achieve, that'll drive those specifications. And finally, most importantly, is the eye box size. And so because most people's interpupillary distance varies as a function of gender, as a function of ethnicity, as a function of age, you have to accommodate the various variations that you see in the IPD or the interpupillary distance. And so having a large eye box, typically greater than 10 millimeters, will allow you to design products that requires very little to no adjustments of the product or the device for the customer's head. So we believe to accomplish this, well, we believe, and a lot of in the industry believe, that laser beam scanning is the ideal solution in order to achieve these key characteristics that we need for smart glasses specifically. Why is that? Because they have a very small micro display, which is enabled by using a laser beam scanned mirror. Second is using a very competent illumination source, a laser, very high performance, high powered laser. And together, you can generate in excess of 10 to the 6 candelas per square meter, 10 to the 6 nits. Quite a lot of light. They said, my God, it's so much brighter than 1,000. Why is there so much? The reason why is that you want to have enough of a photon budget so that when you lose a lot of light through your system, you have more than enough light that can go to the eye that can help you develop and design your systems. And then finally, you want to be at a much lower power here. Again, as I said before, because you want to have very low thermal load as well as very low mechanical weight on your head. And being less than 1 watt, really less than 5 milliwatts, is where we need to be for these kind of products. And finally, in today's technology, in today's world, DOE, diffractive optical elements, or HOE, holographic optical elements, are the ones that are quite popular for waveguides and for combiners. And so these work extremely well with those technologies. So from an overall operational point of view, how does it work? So in this diagram over here, you'll see a photograph of a MEMS Micromirror next to a US 1 cent coin, and also the same mirror packaged into a module. It's quite small. In fact, we're even smaller today than what's shown over here. And how it works is very simple. You basically take 3 lasers, red, green, and blue, to give you the full color spectrum. You collimate the lasers as they come out, rapidly expanding. Then you combine them through combining lenses, dichroic elements, or beam combiners. And the combined beam hits the mirror scans back and forth, and gives rise to the images you can display. That's how it works for laser beam scanning. And so we've taken all that and we combined that into a very small package. This package shown here is in the order of 0.75 cubic centimeters. I'll show you a little bit more details later so they can fit into the temple of your glasses. And then you take that and you instantiate that into the temple of your glasses so that you can very easily and quickly design lightweight, form-fitting, form factor smart glasses. So here is how it really works. So basically, as I said earlier, you've got 3 lasers, red, green, and blue, goes to collimating lenses, go to dichroic beam combiners, hits the 2 mirrors here, 1 horizontal scan, 1 vertical scan, and that raster scan gives rise to an image, which then goes to a projected wall or to your eye through some kind of intermediate medium, such as a combiner or a waveguide. So A little more deeper in the architecture. How does it actually work? What do you need to, in fact, implement this in the architecture? And what are we doing today? There are two components. One is the photonic side, or the optronics module, and then there's the electronics system. So the photonic side is pretty straightforward. It's lasers, it's some intermediate combining, and really optics. It is a MEMS mirrors and some electronics around that. Then on the electronic side, you've got the driver for the MEMS to drive the actual MEMS mirrors. You also have drivers for the lasers. Then you control the entire system, an active feedback control system, and all that together gives rise to the electronics portion for the core driver. And then those are the elements that you see over here in the PCB and in the photonics module, which then gets put into the temple of the glasses and then combined to your waveguide. And so really at the MEMS mirrors, there are three different categories of technologies today. There's electrostatic, there's electromagnetic, and then there's piezoelectric. We are going towards piezoelectric for the future because it's much higher performance and it has much higher resolution and higher scalability. And that's combined with advanced laser diodes. So you want to make sure you have very high rise time, very fast rise time, very fast fall time to have crisp pixels. And then finally, in these systems, you also have to have really optics, which can take the light coming out of the engines and shape them effectively to maximize the input coupling into your waveguides. So we've taken all this, we put it all together into proof of concept, and we put together a demo with some partners of ours that I'll discuss a little bit later. Down below in the left-hand side, you can see basically a little cutout schematic of the laser diode, of the laser beam scanning module. And here's the performance we're actually able to achieve with these glasses. We will have these in our booth here at the expo starting tomorrow, so you can take a look at it yourself. We were able to achieve a pretty high brightness, 1,300 candles per square meter, 1,300 nits. We got a 30-degree diagonal field of view. We hit a 10 by 10 millimeter eye box, and we also had a resolution of 33 pixels per degree. So I want to pause here and talk about language. We talk about resolution in terms of display language, which is wonderful, but it's not a display. So we need to start thinking about a different way of describing resolution to the eye. Talking about 720p lines per inch or lines per millimeter is not useful for this category. So here we talk about pixels per degree. So human eyes, I think around, remember, that's 60 or 66 pixels per degree is maximum resolution. And so we are at about half that, which is quite good actually, and we'll improve this over time. Okay, over here is a photograph. So, I've shown this before at online conferences, which is not at all appealing to some people. Hey, this is what we see. Take a look at a photograph through the glasses. Well, tomorrow, actually go see this for yourself for the first time live. But this is what we showed. I showed it in an earlier conference in terms of the image as taken through the glasses with using a standard cell phone camera. There's some color differences you'll see here because you've got RGB color filters in your camera, RGB lasers, you got waveguides. So that sort of translation through these various medium gives you some color weirdnesses here, but nevertheless, we have very crisp images, very good field of view, very nice, pleasing images. And this is the kind of data and information we think is useful for this kind of device, these kind of products for the future. But again, we will have this in our booth, and I'll welcome you, and I'd love to share this with you. So, this is the current generation, as I mentioned earlier, is a 0.75 cubic centimeter module, volume size module. It is electrostatic mirrors. It has a certain set of parameters that you can read here, which I won't read, but you can read yourself. But we're going to improve that. We're going to transition from electrostatic to piezoelectric, and the reason why is severalfold. We've got a much higher optical field of view, which is important to give enough of a headroom for the designer to design the different systems. We've also increased resolution. I got to change my language here to not talk about 720p, which I kind of break my own code here, but nevertheless, a high resolution. It's a little bit smaller in volume, but most importantly, it'll consume 50% less power than the previous generation. That's really, really important because power is going to drive size and comfort and weight. And so the reason why laser beam scan solutions are really ideal for near-eye display is because when you really think about designing an entire system, you've got to think holistically. And one of the mistakes people are making, in my view, humble view in this industry, is that they're designing things piecemeal fashion. You actually can't do that. You need to think about what am I trying to achieve in the end, what do I have now, and how do I iterate back and forth and optimize the various parameters. So in this example of a radar or spiderweb diagram, you'll see the key parameters: resolution, brightness, size, power, power, weight, and so on. And all these interact. And if you push one and you pull the other, you never optimize all for the maximum benefit. So you got to decide, what do I want to optimize? And based on that, you can then very easily have the system adaptable and scalable using the same architecture but different performance. So for example, if on a smartphone, I can use the same platform for a smaller field of view, much higher brightness, much lower weight, have a monocular, and really address that market. But if I want to go to a much larger field of view, much more immersive experience, then I can sacrifice size and have a helmet, for example. That means I can go to a higher field of view. That means I can tolerate a little less brightness. I can do other trade-offs. So depending upon what you want to do, you have to really think about where you want to give so we design towards your end product. And what's nice about laser beam scanning is the exact same architecture can allow you to scale between those two domains. That's really, really important. The other thing is, as I mentioned earlier, is that power. So when we went from electrostatic actuation mirrors to a piezo actuation, we cut the power by a factor of 10. So over here, very simply put, if you look at the power from an electrostatic-based system as CV squared F for resonant mirrors, for example, we reduce that by a factor of 10 by using energy recovery and charge storage technologies. That's important because now I can increase my field of view slightly, or I can increase my resolution, but still have very low power. And again, you have all these knobs you can turn in the system to allow you to be adaptable and scalable within an envelope of product design. And again, I want to keep banging this drum throughout, is that, when we design these things, you have to actually design this thing holistically. You cannot do piecemeal. We learned the hard way, you cannot do piecemeal. We designed everything and stuck in the waveguide, said, oh my God, it doesn't work now. It doesn't work very well. What did we do wrong? So you got to really think through from the very end of the waveguide back to the laser source in between, say, okay, how do I now design this within this kind of environment? So when you put together an entire set of pair of glasses, a lot of things have to come together. So I talked about laser beam scan engine, but you need more than that, right? You've got the display, of course, obviously. You've got the optics behind the display. You've got the waveguides. You've got applications and application processors. You've got various sensors to do the interaction, the user experience, the user interface. Got a whole plethora of things coming together. And so certainly, as a company, ST, we can do a lot of these. We don't do all of these, but we also have partnerships we created and developed through the industry to make sure that we actually can help the industry be able to go to market quickly with the fully designed end products. And so to do that, we developed something called the Laser Alliance, or the Laser Alliance ecosystem. It takes a village to create this. And AR is still very nascent, it's still very new, even though we've been doing it for a number of years, and these conferences they talk about it all the time. To the rest of the world, it's quite a new category. And to try to develop products with a very rapid time to market and do it in a cost-efficient way and a cost-effective way takes time. So last year, we created this alliance with founding members listed over here. And this past March, we actually launched this officially. And now at this point, we are triple the size, and we're growing as an alliance. And the idea alliance is a nonprofit entity where companies come together. Some are competitive, by the way, but the idea is we want to come together to develop the technology all around laser beam scanning so that we can bring to the marketplace, that is to the OEMs and the ODMs, other stakeholders, solutions, devices, components, technologies that they can rapidly deploy and go to market with. And so if anybody's interested, please come look upon us. And we'll also be here as part of the Laser Alliance booth. And some of the companies on the Laser Alliance will also be part of that pavilion right next to Niantic at the exhibit hall over here. So with that, I'll leave you with a final video here, and I think it'll just wrap us up here. Okay, it brings you up to 10. Thank you very much for your time. I appreciate it. And thanks for hanging in there. And with that, I'm happy to take questions, or if you want to run to your cocktails, I would encourage you to do that as well.
My name is John Papalafere from Thales Defense.
Oh, there you go. Sorry.
One of our concern in using laser is just because of the feel that people have, that if you have laser in your eye,
Sure.
it burns.
Yes.
What is the Alliance doing?
Great question.
To prevent this? That is one.
Okay.
The second one is you have 60 frames per second for the image. Can you do 100?
Okay, so let me ask, I'll answer, thank you for the good questions. Great question on the laser. Yeah, there's mythology. People, oh my God, laser beam, that's terrible, it's scary, it's dangerous. Well, that's not true, right? It can be true, but sun is also dangerous, right? So is halogen lamps. And so from Alliance point of view, the things we do is we also have a whole body of people working on education as well, right? So we have laser safety experts, for example, that are part of the Alliance, and we're developing white papers to say, hey, here's how lasers work. Here's why they're safe. Here's what we do about them. And so we have a whole education campaign that will be coming out within the next few weeks, in fact, or next couple of months even, right? And so we're certainly, from an Alliance point of view, education is really important. So we're going to address laser safety, or it's eye safety in general, not just for lasers, but also any imaging system, right? When you have light coming to your eye, whether it's laser, LEDs, right, halogen, doesn't matter, right? They're certainly going to be careful of. So we are going to be doing that. We are doing that as part of the Alliance. Now, the second part of your question, in terms of 60 frames per second, that's certainly enough for smart glasses. It's not demanding, right? You're not watching movies in real time, for example, right? It's pretty pseudo-static images, more or less. However, when you go into much more immersive and a lot of rapid re-renderings, we can certainly increase that as well. But again, it's a trade-off, right? So if we start to increase your frame rate, where do you want to trade off, right? So something has to give resolution, or something has to give, all right? So the answer is yes, we can, but as I said earlier, it really depends on what's your overall parameter, what's your overall system parameter. Now, I'd be lying if I told you, no problem, I can do that and keep everything else the same. That is just not true for any system, right? So we've got to think through, what is my system goal? And why do I need to get to 100 hertz or 120 or 240, whatever it is? What pain problems is there? Let's think about that is, right? And so if you're seeing some kind of artifacts, for example, we can maybe mitigate some other way. We don't need to go to a rapid frame, it just depends. So the short answer is yes, we can do that, but the longer answer is let's think about what trade-offs you want to make, why you want to be there, and what other methodologies may exist in order to get you the same sort of effect or the issues that you're having because of the lower frame rate, for example. Okay.
Okay. Bill Parker, Creative Micro. Curious about effects of vibration on your system since you have a vibrating element. Mm-hmm. Is there any concern with that?
No, great question. Again, wonderful questions. The answer is no. You think there would be no, but we've developed design systems to go through different levels of shock testing, for example, right? So the answer is no. There certainly is in any kind of micro electromechanical systems, of course, but we designed our systems and packaged it, and then of course test it through what we call a shake, rattle, and roll test, if you will, right? Different shock and vibration both. So the short answer is no, because we designed it for that. We also designed a class of mirrors for automotive as well to take care of those conditions too. But that's a good question. It's a fair question.
Hi.
Thank you. It's okay. I'm like blinded here. Thank you. I appreciate that.
Austin from Boston. That's all you have to
Very nice.
Okay. I was wondering, the field of view for AR glasses are traditionally in the middle of the lens, where people are generally looking. Mm-hmm. I was wondering if you've done any work creating the display in the peripheries.
Excellent. Good one. Great question. The answer is yes, we have, and we can place it within, I mean, that's a really good question. One of the things we're talking with our partner about is that, do you want to be right there in the direct field of view, right? Do you want to be a little offset, right? We think it should be offset. The answer is it can be. We looked at that, and so we need to do more study from a user point of view, saying where do you need to be, right? We can offset it, for sure. And we are actually looking, in fact, I believe the glasses we have below is slightly offset, if I remember correctly. I need to go double check that. I'm pretty sure it's offset. The answer is yes. And so the larger question is, and we need more data here, right? We need to do more user research. Okay, where does it need to be, right? Does it need to be up and to the right, offset this way? Like, where does it need to be, right? And so there's not enough data yet that we've gotten from consumer research, but it can be done, but we need to do more work. Or I would say the product designer needs to do more work to see where it should be, right? We're sort of agnostic to where it can be.
Sorry, a really quick follow-up.
Sure.
So this is hardware. With software, you generally have a user, you have an engine like Unity so that somebody can just make their own solution. So is there any work with the lens space or optic space where you're going to create a sandbox for people to make their own optic solution given their own needs? So something that I ran across recently was, if you're going to give a doctor an AR headset, they need it to be as unobstructive as possible. So maybe they want to play with the opacity, or they want to put it off to the side rather than put it in the middle. So I was wondering if anyone in Star Alliance is working on a sandbox for creating your own optic solution rather than just creating a optic solution.
Answer is no. It's a great idea. We haven't done that. We're not that far mature yet as an industry even, right? It's a great idea. And the short answer is no, we haven't done that. But I think it's an interesting idea, and I'd love to take it. Being also chairman of the Alliance, I'd love to go back and talk with the team, right? Go with the member company and say, hey, what do you think of this? It's an interesting idea. I don't know how you do it. I need to think about it, but I like the idea, certainly. But the short answer is no, we haven't done anything yet because we're so early on in this industry, and that we need more guidance. In fact, we need more feedback from end users as well, right? Because right now we're looking at it very strictly from an optomechanical display kind of perspective, which is really important. But as I said, it's a holistic system, right? We need to get more feedback as well from the other side. So the answer is no, but, right?
So for actually follow-up, kind of attached to the question is how is the kind of current solution for mitigate the field of view? Because I know when you shifted your eyeball, it's causing kind of deviation of the vision of the laser beams imagery. So I was wondering, is there any kind of potential solution for such as eye tracking to mitigate that sort of laser view?
Well, right now, I'm not sure I know what you got to mean. We may take it offline, but let me ask the second question first. Right now, we don't see any kind of issues that you mentioned. However, having said that, in terms of eye tracking, there absolutely is. There's a partner in the alliance, called Highway Vision that we're working with, and then they worked on developing a solution with dynamic eye tracking and foveated rendering, for example, right? Which is another way of implementing laser beam scanning solution, for example.
How kind of benefit? Because HoloLens 2, we know there's a rainbow, really terrible image color accuracy.
Okay, I know what you mean. Okay.
Accuration of that.
I see the question. Okay, so a couple of things. So in the world of waveguides, obviously there's trade-offs to make, right? So it's diffractive or holographic, all the kinds of waveguides. Depending on size, if the larger field of view, the more aberrations you may get, right? Particularly the edges. You're absolutely correct. And so big companies, small companies, alliance members are all working on trying to mitigate that from an optical design perspective in other ways, right? So that's going to happen, and that's going to improve over time, and it's going to get better and better and better. Is it there today? No. Will it get better? Yes. And lots of money is being put into that. So put that aside. If you go to a different schema, such as direct retinal scanning, that's a whole different paradigm, right? There you don't have optics anymore. It really, there's no sort of combining optics such as a waveguide, right? I'll call it a waveguide-less system, okay, in a sense. An eye-box-less system, in fact, because you do people tracking. So when you do people tracking, then you get rid of all those things, right? And then all you do is just basically, follow your eyeballs, follow your pupil, right? And deliver the content and paint your retina. So that's solved a whole bunch of problems. So that's sort of the end game eventually, right? Or one end game certainly, right?
Thank you. You were raising your hand.
What about like foveated vision? So you don't technically have to have resolution over
Exactly.
the whole thing. So you
Yep.
could do eye tracking and
Yes.
then look at and
Yep.
implement foveated
Yep.
vision.
So as mentioned earlier, one of the companies on the Alliance, Highway Vision, in fact, developed that, right? They developed, basically dynamic eye tracking with foveated rendering, right? So that way you can reduce your compute bandwidth quite a bit, but delivering the highest fidelity, highest resolution to foveated vision and lower for out here, right? And it works really, really well. So yes, that is being worked on.
Have you looked at like the power saving of that?
haven't,
Or the
what,
speed of the frame rate or anything like that?
I know they have. I know I can certainly put you in contact with those guys. You should talk with them, right? So they've done a lot of that work. And the answer is yes. We haven't directly, but they certainly have done a lot of work. And they've been doing it for, gosh, I don't know, 5, 6, 7 years already. So it's got a bit of work there. Okay.
Thank you very much.
Thank you, guys. I appreciate
Yes,
it.
thank you.
Thank you for hanging in there. I really appreciate it.
Well, we just want to thank our gold sponsors for their support: Artboard, XR, Care, AR, Xerox Company, HP, Metamaterials, Plug, XR, and a big thank you to our titanium sponsors, Niantic, Qualcomm, and Unity Technologies. And thank you, everybody. See you at the happy hour. I'm not a party person. No. Thank you, and thank you. What a good track. Congratulations.